All right, thank you. All right, so let me start again. So this chapter is on magnetic field. Okay, so let's represent by defining magnetic force. Magnetic force. This is force between current carrying objects. Force between current carrying objects. Current carrying objects, which means motion of charges. Okay, so if you have two wires carrying currents like this, there will be magnetic force between them because of the motion of charges in those wires. Okay, and then we have magnetic field to represent magnetic force. The field just makes it a property of space. Okay, that's the purpose of a field. You've got a certain value uh, representing a certain point. Okay, so this represents magnetic force. Represents magnetic force, and the unit of magnetic field is called Tesla. Tesla, and that's abbreviated by capital T. Okay, we can also represent field with field lines. So magnetic field lines. These are lines that represent magnetic field. These are lines that represent magnetic field. Represent magnetic field. Now, how do lines represent the field? The field is a vector. So you remember the same thing like electric field. The magnitude of the field is represented by the density of the lines, or by the number of lines per unit perpendicular area. Okay, so this is represented by the density of the lines, represented by the density of the lines, density of the lines. Okay, um, for example, let's say if you have this kind of field, what that means is the field is stronger over here than over here, because the density of the lines is bigger over here. Okay, so the magnitude is represented by the density of the lines. How about direction? For direction, first of all, the line of action is the parallel to the line tangent to the curve. Okay, the line of action of the field, line of action of the field is parallel to the tangent line, is parallel to the tangent line. Tangent line. Okay, so let's say you have this field over here, and you're looking for the direction of the field right over here. The line of action of the field is parallel to this tangent line. Okay, but it could be this way or this way. To distinguish between these two possible directions, you put an arrow on the line. So if I put an arrow over here, it means we pick this direction over here. So with these two rules, you can determine the direction of the field. Okay, arrows are used to distinguish between the two possible directions. To distinguish between the two possible directions. The two possible directions. So with that, you can represent the magnitude and the direction of the field. Now, one important property of magnetic field lines, which is different from electric field lines, is if you remember electric field lines, they start from positive charge and they end up in negative charge. Remember? They go like this. They originate in a positive charge and they sink in a positive charge. But we don't have magnetic charges. So magnetic field lines form complete loops. Okay, magnetic field lines, they form complete loops. So one important property is magnetic field lines form complete loops. Form complete loops. Okay, there will be something like this. All right. So these are general properties of fields. Now, let's look at permanent magnets. So we've said that the origin of magnetic field is motion of charges. So what do you think is the cause for the magnetic field is a permanent magnet?
the field of the aligned
You
charges
see,
in the
there are
atom.
electrons. It's due to the motion of the electrons. Okay, so this is due to the motion of electrons around the nucleus. This field is the field due to the motion of electrons around the nucleus. The motion of electrons around the nucleus. Okay, according to the Rutherford model of the atom, you got the nucleus center, you got proton neutrons, and then you've got electrons revolving around, right? So you got motion of charges. That's the cause of the magnetic field due to permanent magnets. But you can say that all elements have electrons, but not all elements are magnetic. The magnetic elements are like nickel, cobalt, and iron. The reason is, you see, this electron will have its own magnetic moment or magnetic property. So for most of the elements, the magnetic properties, these all the electrons, they cancel each other. Okay, all the electrons have magnetic properties, but when you combine all of them, their magnetic properties cancel each other. Only for certain elements such as cobalt, nickel, iron, you got a net magnetic property for the atom. Okay, so that's the reason only few elements are magnetic and the other elements are not magnetic. Okay, so the magnetic elements are iron, cobalt, and nickel. Now you can also say that, let's say you have iron. Iron is magnetic, okay, but a normal iron sample is not magnetic. What's the reason? Well, each atom has a magnetic property for iron. But normally those magnetic properties, the magnetic moments are vectors. They are oriented in random directions like this. So normally they will cancel each other, okay? Because the magnetic moments of each atom are arranged randomly, so they cancel each other. But if you put this in an external magnetic field, what happens is, you saw in the experiment, you have the iron filings. When you shake it, they rotate in the direction of the field, right? So if you put it in an external magnetic field, what happens is these magnetic moments, they are arranged in the direction of the field. They will go like this, okay? So because of that, you get a net magnetic field. The iron becomes a magnet, okay? So that's the reason a normal iron sample is magnetic, but if you put the magnet in an external magnetic field, it becomes a magnet, okay? The atomic magnets are aligned in the direction of the external field, and that makes it magnetic, okay? Now let's talk about poles, magnetic poles. Now for certain permanent magnet, there are two places where the magnetic field comes out and the magnetic field comes in. Let's say you have, you've seen the experiment we did last time. If you have, let's say, rectangular uh, magnet like this, as you see in the iron filings, the fields, they would be, they will come out over here and they will come in over here, okay? So you have like this, and they'll come in over here, back over here. They form complete loops, right? And then you have over here like this, they come out of one end and they come in into the other end, okay? So there are two locations where the magnetic field lines come out and the magnetic field lines come in, okay? These two locations are called the poles of the magnet, all right? The point where the magnetic field comes out is called the north pole, and the location where the magnetic field lines come in is called the south pole, okay? So, but how are the north and south pole defined? Well, Earth has its own magnet, okay? So let's say this is Earth. This has its own magnet. It's directed along the north-south, but it's a little inclined, but it's directed along the north-south pole, okay? So if you let an iron, I mean a magnet, rotate freely about a pivot, what's going to happen is it's going to align itself in this direction. Okay, if you let a magnet rotate freely along a pivot, it's going to align itself in this direction. Okay, so the the end of the magnet that points towards the north pole of Earth is called the north pole of the magnet, and the end that points towards the south pole of Earth is called the south pole of the magnet. Okay, now as you've seen the experiment, opposite poles attract, similar poles repel, right? So we have this general relationship, opposite poles um, attract, and similar poles repel. Similar poles repel. Okay, so if you have defined this as a North Pole, then what do you think this will be? This is being attracted to this end of the Earth, right? So this should be the South Pole of the Earth's magnet. So what Celsius is, according to this definition of the poles, then the South Pole of the magnet is located in the geographic north. So this is the south pole of the Earth's magnet. This is the north pole of the sun magnet. So what Celsius is the uh, south pole of Earth's magnet is located geographic north, and the north pole on the south of the magnet, the north pole is located in the geographic south of Earth. Okay, so the conclusion is south pole of Earth's magnet is located in the geographic north. In the geographic north, uh, and geographic north. And similarly, of course, the North Pole is located in the geographic south. Okay, and the North Pole is located in the geographic south. It's just because of the way we define the North Pole of the magnet. Okay, if you say let the North Pole of this magnet be the one pointing towards this end, it's being attracted to this one. So if we say this north, this must be south. Okay, so because of that, the south pole of Earth's magnet is located in the geographic north, while the north pole of the magnet of Earth's magnet is located in the geographic south. Okay, since there are some of the qualitative aspect of it, so now we're going to move to the uh, quantitative aspect of it. We're going to look at the magnetic force on a charge moving in a magnetic field. Okay, magnetic force on a charge moving in a magnetic field, in a magnetic field. Okay, now first let me tell you a little bit about the direction of the magnetic field. In the case of electric force, you see the electric force and the electric field, they have the same line of action. They have the same direction, the charge positive. They will have opposite direction if the charge is negative. But in this case, there's velocity involved in the force. The force depends on the velocity. This is force due to motion of charges. So that's not simple. So let's see how we define the direction of the magnetic field. Suppose you've got a magnetic field over here, okay? Suppose you have a certain magnetic field over here, and you've got charge moving in different directions over here. There is certain direction of the velocity that doesn't experience any force. Okay, if you've got charges moving in different directions over here, there'll be one direction where there is no magnetic force. That direction is defined to be the direction of the magnetic field. It's the direction where no magnetic force is experienced. Okay, you saw in the experiment, you see we have iron filings listed. When you check them, they point in a certain direction. That's a point where they are at rest, where they don't experience any torque. Okay, so the direction, let's say you've got this all randomly oriented magnetic moments of the iron filings, but when there is a magnetic field, when there is a magnetic field, they're going to be at rest in a certain location. Okay, so that point where they are at rest in a certain location is a location where they don't experience magnetic force or magnetic torque. Okay, so that is defined to be the direction of the field. The direction of the field is the direction where a charge moving in that direction does not experience any force. Okay, so now let's say you have this field over here, okay, and then you have an arbitrary velocity over here. So what this means is, you see, we can decompose this into two parts, into v parallel and v perpendicular. Now, by definition, this component does not experience any force. Okay, the component, the field in the this is the field over here. The component of the velocity in the direction of the field does not experience any force. So it depends only on the perpendicular component of the velocity. Okay, so let's look on what factors the force depends. Let's call it FB. This is proportional to the charge of the particle, is proportional to the charge. Of course, it's proportional to the strength of the field, But then it depends on the perpendicular component velocity. It doesn't depend on the component parallel to the field. Okay, V perpendicular. All right, those are the three factors it depends upon. So it's actually defined to be like this: charge times field times V perpendicular. Okay, this is magnitude, so we can put this in absolute value. Now, suppose the speed is V, this is theta. Okay, so this component V perpendicular is the speed times the sine of theta. Okay, so the magnetic force is actually defined to be the charge, the speed times V times the sine of theta. Okay, this is how we calculate the magnetic force on a charge moving in a field. Okay, so we have two vectors over here, the velocity vector and the B vector. What formula does this remind you? What kind of product? Cross product or dot product?
Cross product.
Cross product. So generally, this is actually, you get the charge, and then you have the cross product between the velocity and the field. Okay, this is the vector definition of the magnetic force. It is charge times the cross product between the velocity and the field. Okay, so from this equation, if you take the magnitude, you just get this one. Okay, now can you tell me about the direction of the force in relation to the velocity and v? You remember the direction of a cross product? The direction of a cross product is usually perpendicular to the plane determined by the two vectors. Okay, so in this case, this is the velocity, and this is the field. This determines the plane of the paper. Okay, so the direction of the force of a cross product is perpendicular to the surface. So it's going to be either perpendicular out or perpendicular in. Okay, so direction of the force is always perpendicular to the plane determined by the velocity and the field. So the direction is perpendicular to the plane determined by the velocity and field vector, by the velocity and field vectors. Okay, so there are two possibilities. It could be perpendicularly out or perpendicular in. That is, it's either perpendicularly out, remember it's represented by dot, or perpendicularly in, and that's represented by a cross. Okay, now if you represent the velocity and the field in the ij notation, you can use mathematics to do this. If this is I and this is j, the direction will end up being k. Okay, but we can also do it using the screw rule and the right hand rule. Remember those two rules? Let me go briefly through them to distinguish between the perpendicularly out or perpendicularly in. You can use the screw rule, either the right hand rule. Okay, let's look at the screw rule. In this case, what you do is you connect the two vectors tail to head like this. Let's say this is V, let's say this is B. Okay, and then you put a screw perpendicularly at this intersection point. Okay, and then you rotate the screw from the first vector, which in this case is V. In this formula, V is the first vector. V is the first, V the second. Okay, so you're going to rotate the screw from the velocity vector toward this, the field vector. Okay, now remember, a screw goes in if you turn clockwise, goes out if you turn counterclockwise. Okay, then if the charge is positive, the direction of movement of the screw gives you the direction of the force. But the direction negative, you gotta reverse it. That's times a negative. Okay, so if Q is positive, if Q is greater than 0, direction of movement of the screw gives you direction of the force. Okay, direction of movement of screw gives you direction of force. Okay, and if Q is less than 0, it becomes opposite. Okay, opposite to the direction of movement. Okay, to the direction of movement. So that is the screw rule, the direction of movement. Just remember, you rotate your screw from the velocity vector towards the field vector, okay? So in this case, what do you think the direction would be? Would it be perpendicularly out or perpendicularly in this case?
In.
In, because this is clockwise, okay? If you turn the screw clockwise, it goes in. So in this case, it will be perpendicularly in or across, okay? But if you wrote like this, let's say this was B, this was V, you see? I'll put my screw over here, and then I'll rotate from V towards B, like this, okay? That is counterclockwise, and the screw comes out, right? So in this case, the direction will be perpendicularly out or that, okay? Remember, cross product is not commutative. V cross B is a negative of B cross A, okay? So this is one way of doing it. And then we have the right hand rule. Right hand rule. Right hand rule. So in this case, you represent the velocity vector, let me over here, by your index finger. You see, this represents velocity, this represents the field, and then thumb, which is perpendicular to them, represents the force, okay? So in the right hand rule, velocity is represented by index finger, and the field is represented by middle finger, and then of course the force is represented by thumb, which is perpendicular to them, okay? So you have to use your right hand, and you have to make sure you align the index finger in the direction of the velocity, and the field in the direction of the middle finger, and then the thumb gives you the direction of the force. You just try and find out is perpendicular out, perpendicular in. Okay. So in the example we saw, let's say this is V, this is B. Okay. So you see, this one has to be in the direction of the velocity, and this one has to be in the direction of the field. Okay, I don't know, but you see it. So your thumb goes down, so it's perpendicular in. So you put your index finger through this vector, and then reverse vector this way, and then thumb goes down. Okay, do you see that? So direction will be perpendicularly in, If you reverse them, if this is B and this is V, then you have to make this the V, I mean the index finger direction of the V, and this one direction of the V, then thumb points up. Okay, so you get perpendicularly out. I prefer the scroll rule, but most people like the right hand rule. Okay, so this will be perpendicularly out. So just align the velocity vector, index finger, and the field vector, the middle finger, then thumb will give you the direction of the force. And of course, if the charge negative, you reverse it. Okay, so that's how we calculate force exerted on a charge moving in a magnetic field. Okay, let's consider some examples. Suppose, let's say we have the following field. Let's say this is, the field is perpendicularly out. Okay, let's say the field is 10 Tesla, and then let's say we have a charge moving this way. Let's say the charge is positive, Q equals maybe 2 Coulomb, all right? And let's say the speed is maybe 100 meters per second, all right? So first let's do the magnitude. Okay? The magnitude is FB equals charge times speed times B times the sine of theta, okay? So we have the charge, which is 2 Coulomb. We have the speed, which is 100 meters per second. We have the field, which is 10 Tesla. We just have to figure out the angle. Can you tell me what the angle is? You see, the field is perpendicularly out, but the velocity is to the right. So what's the angle?
90 degrees.
This is the velocity, this is the field. What's the angle between them? You see, The velocity is parallel to the paper, to the right, but the field is perpendicular to the paper. So what's the angle between the field and the velocity?
90.
90 degree, okay. So our theta is 90 degree. So we have theta equals 90 degree. And so FB would be simply the charge to the speed 100, the field 10, and then sine of 90, which is 1, okay? So I think it's just 2000. All right, so you get 2000 newtons over here, okay? Now let's look at the direction, okay? So the field, is perpendicularly out. Maybe is it better over here? Let me do it over here. So the field is perpendicularly out of the paper. This is the velocity, okay? Now you put your screw at the intersection point, you got to rotate from the velocity towards the field. That is from my finger, which is the velocity towards the field. So I'm turning, can you see that? Counterclockwise. Do you see that? You got the field up, you got the velocity going this way, you put the screw at the intersection point. When you rotate from the velocity toward the field, that is in a counterclockwise direction. And the screw comes out. Okay, so what do you think is the direction? Will be south. Okay, so you have the velocity going up. You got this parallel to the paper, and then you rotate your screw from the direction of the velocity toward the field. The screw comes out because counterclockwise, and thus down the paper south. Okay, how about using the right hand rule? You see, this is the velocity. This goes this way. The magnetic field, see what happens? The magnetic field is up, the velocity is this way, and thumb points towards me, towards down of the paper, which is south, okay? The direction is south. But you can do it mathematically very easily. So let's try it mathematically. Remember, perpendicularly out is K. K cross is negative K, okay? And of course, south and north are J negative J, and east and west are I negative I, okay? So let's do it mathematically. So in this case, what do we have? We have the velocity going to the right, so that's in the I direction, right? So we have the velocity vector is 100 in the I direction, okay? How about the field? The field is up, which means in the K direction, right? So that is 10 in the K direction, okay? So the force is charge V cross B, okay? So we have, well, I'm just looking for direction, but anyway, so the charge is 2, and then you've got the 100 in the I direction, cross it with 10 in the K direction. Basically, I cross K, okay? So 2000, and then you've got I cross K. What is I cross K?
Negative J.
Negative J. You remember that rule? You have I over here, J over here. Oh, you're going to counterclockwise. You got I over here, J over here, K over here, okay? The cross product is the other unit vector. But if you go in a counterclockwise direction, you get the positive. If you go in a clockwise direction, you get the negative. So in this case, this is our I. So we're going in a clockwise direction. Okay, so you get negative J. Okay, so this is 2000 in the negative J, which is south on the paper. Okay, so direction of the of the vector is south. So if you can represent them by A and J, that will be much easier. Otherwise, you can calculate the magnitude using this formula, and then you can use either the screw rule or the right hand rule to get the direction. All right. Now we're going to look at magnetic force on a current carrying straight wire. Magnetic force on a current carrying straight wire. Current carrying straight wire. Okay, so let's say we have this magnetic field over here. Okay, let's say this is B. And then let's say we have this current carrying wire over here. Okay, so this is a motion of charges, right? So if you take a little bit amount of charge over here, okay, dq, let's call this dq. And let's say this charge is moving with speed v, okay? And let's say this displacement over here in time interval dt is, let's say, dl, okay? So the force on this charge over here, according to our definition, let's call dfb, would be, we have the charge dq over here, and you've got the velocity. Velocity is the displacement divided by time, right? So you've got dl divided by time would be the velocity, right? Cross b. That's what this is, okay? But we can move this around. We can write as dq by dt, and then you've got dl, the small displacement over here, cross it with b. What does this represent? Charge divided by time. Charge per unit time, or rate of flow of charge. What do you call it? What is rate of flow of charge?
Current.
Current, okay? So but dq by dt is current, okay? So we have this formula. So this force on this small charge element is current times the small displacement delta L over here, cross it with B, okay? To get the total force, we just integrate. So the total force is the integral of dfb, okay? Which is, we can take the, well, let's say the integral of I dl cross B, okay? Now, if the I and the current are constants, we can write like this one, current, okay? And then the integral of dl, okay? And then cross B, okay? What's the integral of dl? This is like dr, okay? You just get delta L, okay? Let's say this goes from position vector Ri. Let's say I have this coordinate system over here. Let's say this is Ri. Let's say this is Rf, okay? So what you get is Rf minus Ri, which is this one, all right? So dl is represented by delta L. It's just the straight line connecting the initial point and the final point, okay? So this equals, so we have the force, the magnetic force is current times the displacement delta L cross this B. Now, the current has a direction. I'm going to put the direction in delta L. Delta L will have the direction of the current, okay? So I'm going to put this in absolute value, and the direction of delta L will be the direction of the current, okay? So in this case, if the current is going this way, this would be delta L, okay? But if the current is going the other way, delta L go this way, okay? The direction of delta L would be the direction of the current, all right? Now, it's very important, over here, it doesn't matter what the shape of the wire is. It doesn't matter what the shape of the wire is. The integral of dl is simply this line. This line is delta L, okay? So delta L is simply the vector connecting the initial point, the final point. It's a displacement, okay? Because when you integrate this from Ri to Rf, what you get is Rf minus Ri. It doesn't matter what the shape of the wire is. It's simply a straight line connecting the initial point and the final point, okay? And the direction of that displacement is the direction of the current. If the current is going this way, it will be this way. So in this case, let's say if the current is going this way, so your delta L will be this vector. This goes this way, it will be this one. This will be delta L. If the current is going this way and going the other way, it will be this way, okay? So direction of delta L is direction of I. Direction of delta L is direction of I. And then we just put the current in absolute value of I because we put the direction on delta L. Okay, so that's how we calculate magnetic force. It's current times the cross product between delta L, that's the straight line joining the endpoints of the wire, crossed with B. Of course, now the magnitude will be like this. It's a cross product. So the magnitude would be I magnitude of delta L, this is delta L, B sine theta, okay? Where theta is the angle between the field and, so in this case, this will be theta. Angle between delta L, the displacement, and the field will be this one, okay? So this would be the magnitude. How about the direction? Well, it's just a cross product between delta L and delta B, okay? So if you use the screw rule, you have to rotate from delta L towards B, which means from the direction of the current towards B. If you're using the right-hand rule, you have to, this would be now current, okay? The index finger is current, the middle finger is B in this case. The only difference is this one becomes current instead of velocity. The field remains the same, and this gives you the force, okay? So for direction, if you use the screw rule, rotate from direction of current to field, direction of current to field, okay? And if you use the right-hand rule, the only difference is the index finger is represented by current, okay? So index finger will be current, okay? And middle finger would be field, okay? And then of course, thumb will give you force. Thumb will give you force. Okay, now let's look at an example. Suppose we have the following field. Let's say the field is going like this. Okay, let's say this is B equals maybe 5 Tesla. All right, and then let's say we have this this quarter of a circle like this. Okay, let's say we have this coordinate system over here. Let's say the radius is maybe 2. This is 2. This is 2. This is a quarter of a circle. Okay, maybe let's use this coordinate system over here. All right, so this point over here is 2, 0. Okay, and this point over here is 0, 2. All right, let's say the current is going this way. All right, let's calculate the magnetic force acting on this one. Okay, so remember, delta L is the vector connecting these two. Okay, this is delta L over here. It doesn't matter what the shape of the wire is. This would be a delta L, this one over here. Okay, so delta L in this case is this vector minus this vector. Okay, that is, this vector over here is 2 in the I. Okay, and then this vector is 2 in the J. Okay, so this is my delta L. Do you see that? This vector over here, or you can just say it's 2 in the I, negative in the J. This is vector over here. You've got downward, negative in the J, on, and 2 in the I. So this is my delta L. That's what I need for this calculation. All right, so that's my delta L. And I've got my B. My B is to the right. That's 5 in the I. That's all I need. Okay. And let's say the current is maybe 2 amps. Okay. So we have current, we have field, and we have delta L, we have B. Okay. So we can do the force now. The force is absolute value of the current, and then delta L crossed with B. Okay. So I've got 2 for the current. Okay. And my delta L is this vector over here. That is 2I minus 2J. Okay. And I cross that with 5 in the I. Okay. So you see, what's I cross I? What is I cross I? What do you get if you cross 2 identical vectors?
0.
0. They're parallel, 0. How about J cross I? You know, I cross J is K, and J cross I is going to be negative K. Okay, so what I have is like this: 2 times 2 times 5, that's 4 times 5, that's 20. And then you've got negative j crossed with I. Or let's say let's put the negative outside. But j cross I is negative k, so you get negative 20. And then you've got negative k over here. Okay, so you get 20 in the k. So the force exerting this one is perpendicularly out in the k direction. Okay, all right. So that's how we calculate magnetic force on a current carrying wire. It is delta L crossed with the magnetic field, and then of course times the current. Now, we're going to look at torque on a current carrying loop. Torque on a current carrying loop. Carrying loop. Now, first, let me try to show you why a current carrying loop. Torque is rotation, you remember, right? So let me show you why a loop and a magnetic field will rotate. Okay. For example, let's say we have this loop over here. Let's say it's carrying current in this direction. So the current going this way. We're talking about loops now. And let's say we have magnetic field over here. Okay. Now, what do you think would be the force on this wire? You see, they're opposite. The angle between these two is 180. All right. So sine of 100 is 0. So there is no force on this wire. The same thing over here. The current and the field are parallel. The angle is 0, no force on this wire. Okay? If the velocity in the direction of the field, there is no force. Now let's look at this wire over here. The current is going this way. The current is going this way. The field is going this way. Now, if you use the screw rule, you rotate from the current towards the field. You see that? And that is clockwise, right? You're rotating clockwise. And so the force over here is perpendicularly in. The magnetic force is pushing it down. How about on this side? But now you see the direction of the current has reversed it because it's come this way and we got the field over here. But now when you put your screw and you rotate from the current to the field, you're going counterclockwise. Do you see that? So counterclockwise perpendicularly out. So you see what's happening? This side is being pushed down. This side is going to push it up. So it rotates. Okay, that's why we have, that's why a loop placed in a magnetic field is rotates. But the net force acting on this wire is 0. Can you tell me why? The net force on any loop is 0. And let me ask it this way. For a complete loop, what is delta L? You start at this point, you end at this point. What is delta L?
0.
0, that's why. So delta L is 0, so the force will be 0 because the force is delta L cross B, okay? So force on any closed loop is 0. What you have for a closed loop is torque. It rotates, okay? All right, so now let's try to get an expression for it. Suppose, let's say we have some irregular shape over here, and let's say this is our axis of rotation. Let's say a small element over here. Okay, so let's say this is our perpendicular, okay? The position vector with respect to the axis over here, okay? So the torque is going to be position vector crossed with the force, right? So let's calculate an expression for the torque for this element over here. Let's call it d tau, okay? That's going to be the position vector, our perpendicular, crossed with the force acting on this small wire element over here, okay? And what's DFB? DFB is current times DL crossed with B, right? So we're doing this cross product. To get this torque, we have this vector crossed with the following. You've got current, you've got this DL over here, this small path element over here, crossed with the magnetic field. Okay? Now, to get the total torque, we have to integrate, right? This equals d tau. That is, we do the same thing for all these path elements over here, and we add them together, right? So we have the following. This is the integral of r perpendicular crossed with dl crossed with b. But we have b over here. Okay, it's ideal cross b. Well, this is the force. Okay, I have dl cross b. All right. So I forgot the count. Okay, so the counts, let's say it's a constant. We can take this out. And then you've got r perpendicular cross with dl. And the magnetic field, let's say, is a constant. We can take it out. Okay? Now, what does this represent? What does the cross product between two vectors represent? Do you remember? If you've got A over here, if you've got B over here, geometrically, what does A cross B represent? Is the definition of area. This is the area of this parallelogram. Okay? The area of this parallelogram is AB sine theta, which is A sine theta over E times B. All right? So this basically is this area over here. You see? R perpendicular cross DL is the area over here. So if you add all these elements over here, what do you get? You get total area. So this is the total area of the loop. Okay? So that gives us the formula for torque. Torque is simply the current and then times the cross product between the area and the field. This is the formula for torque on a loop, place it in a magnetic field. Okay, now we're going to leave the direction of the current in the eye itself. Okay, so I is going to be positive if it's counterclockwise and negative if it is clockwise. We're going to keep the direction of the area, as you remember, fix it as perpendicularly out. Okay, the direction of the area is not going to depend on the direction of the current. We're going to put the direction on the current. Okay, this one will always be perpendicularly out. Okay, so I is positive for counterclockwise, okay, and negative for clockwise, all right? And the direction of A, you remember, we did it very extensively in Gauss law, okay? Direction of A is always perpendicularly out. Of A is always perpendicularly out, okay? Perpendicularly out. If you're not sure, what you do is you put your fingers in the area like this, and thumb will give you the direction of the area, okay? So the direction of area is always perpendicularly out, okay? So this is the formula for torque. All right, so let's consider an example. Let's say we have this circle over here. Let's say it's carrying current in a clockwise direction. Let's say this is 2 amp, okay? And let's say we have this field over here. This field over here, let's say B is maybe 5 Tesla. All right. And let's say the radius of the circle is 1 meters. All right. So A, let's say, obtain the torque acting on the loop. Obtain the torque acting on the loop. Okay. So, well, torque is IA cross B. Okay, this is IA cross B. So we just have to obtain these values. Okay. I is, what's the value of I? Can you tell me? What is I? This value is 2, but is it positive or negative? Remember over here? Negative for clockwise. Okay? So I is negative 2. All right? So we have I is negative 2 amps because it is clockwise, right? How about the area? Well, its magnitude is pi times radius squared. Well, let's say the magnitude over here. That is simply pi. Okay, so the magnitude is pi. But what's the direction of A? Can you tell me? What's the direction of the area of this loop? It's always perpendicularly out, right?
Out.
Direction of area. So that's a dot, which means K. Okay, so in this case, you see, put your fingers like this, it's going to be perpendicularly out. Okay, so direction of A in this case is perpendicularly out, which means a K. Okay, so direction of A is perpendicularly out, which means K, in the K direction. Okay, so we have the following for the area. Area is pi r squared, which is pi in the direction of K. Okay, this is our area. And we've been given the field. The field is 5 in the I. Okay, the field is 5 in the I. Okay, so that's all we need. So the torque is I A cross B, right? So that is the current is -2. Okay, the area is pi in the K direction, crossed with B, which is 5 in the I direction. Okay, so we have -2 pi. What is K cross I?
J.
No, I cross, yeah, K cross I is J, you're right, you're in J. All right, so this is 2 pi in the negative J direction, or south, okay? This is 2 pi in the south direction, all right? So the direction of the torque, for this case, is this way. All right, that's the direction of the torque, south. But we want to know which way is rotating. Is it rotating clockwise or counterclockwise? Now, the direction of rotation and torque are related by the right-hand rule. You see, if this is the direction of torque, this gives you, I mean, if this is the direction of torque, this gives you the direction of rotation, okay? So direction of rotation, let's ask, is it rotating clockwise or counterclockwise? Is it rotating clockwise or counterclockwise? Counterclockwise. Okay, well, let's say direction of torque and direction of rotation, that's whether clockwise or counterclockwise, of rotation are related by the right-hand rule. By the right-hand rule. So do you think it's rotating clockwise or counterclockwise? Look, if it was north, it will go counterclockwise, but if it's south, it will go clockwise. Okay, do you see that? If it was north, then you do like this, that's counterclockwise, right? But if it's south, let's reverse it. It goes in a clockwise direction. Okay, so the direction is clockwise. So with that, the answer is clockwise. This loop is rotating clockwise, not like this, but it's rotating like this. It's rotating the other way around like this. Okay, so the answer for this one is south. I mean clockwise. So answer is, this implies clockwise. Okay, we did this mathematically, but let's try to do it using the screw rule or the right-hand rule. Okay, so what do you have? Well, in calculus is magnitude by AB sine theta, so and that's trivial. But how about the direction? Well, the direction is A cross B. So if you want to use a screw rule, this is going to be thumb is going to be your A. Okay, and the field is going to be middle finger, and this gives you torque. Okay, if you decide to use the screw rule. If you want to use the right-hand rule, this would be area. This would be area. This would be field. Okay, and this will give you the direction of the torque. Okay. So with that, if you have field this way and the area this way, and you rotate from area towards the field, what do you get? Well, that is clockwise. It goes in, okay? Look, you got the field going this way. You got the area perpendicularly out like this, okay? If you rotate from the area towards the field, it goes in. But remember, it's clockwise, it gets reversed. So it goes up north, but the current is clockwise, then you take the south direction, okay? So, but usually if you can represent it in INJ, that's much easier. But if you rather use the scroll rule or the right hand rule, that's how you do it. Just remember, this one is A, this one is B, and this one is the field. And if you're using the screw rule, you rotate from the area towards B. In the cross product, usually you rotate from the first to the second. In this formula, area is first, B is second. So you rotate from A towards B. All right? Okay, I think let's take 5-minute break, okay? We'll come back in 5 minutes. All right. So next, we're going to define a property of a current carrying loop. It's called magnetic moment. So let's define magnetic moment of a loop. Magnetic moment of a loop. This is to a loop as a charge is to a charge. It's basically a property of a current carrying loop. It's defined to be the product of the current and the area. Okay, it's defined to be the product of the current and the area of the loop and the area of the loop. Okay, so we're going to use mu to represent it, this vector over here. So we have mu equals current times area. Okay, this is a definition of a magnetic moment of a loop. This is the property of a loop. It's like the mass for gravity, charge for electricity, and this one is for magnetism. Okay, it characterizes the property of the loop. All right, so remember, the area is always perpendicularly out, okay? So when the current is counterclockwise, this is positive, okay? So when the current is counterclockwise, the magnetic moment is parallel to the direction of the area. But when the current is clockwise, this is negative, okay? So the direction of the magnetic moment and area will be opposite when the current is clockwise, okay? So mu is parallel to A if I is counterclockwise, okay? And is anti-parallel to A if I is clockwise, okay? So now we can modify the formula for torque. This is a formula for torque. Torque is current times area crossed with B, okay? But now this is magnetic moment, okay? So the modified formula for the torque will be magnetic moment of the loop crossed with magnetic moment of, magnetic field. So this would be the definition of torque using magnetic moments, all right? So example, let's say we have this loop over here. Let's say it's carrying a current of 2 amps over here. Let's say the radius is 1. The question is obtain its magnetic moment. Obtain its magnetic moment. Okay, so can you tell me what the current is? Mu is current times area. Okay, so what's the value of the current? 2 in a clockwise direction. So what is the value of the current? Clockwise is negative or positive? Negative. In physics, usually counterclockwise is positive, clockwise is negative. Okay, counterclockwise is the positive direction, clockwise is the negative direction. So our current is -2. So our current is -2 amps. The reason is clockwise. Okay, how about the area? The area is, it's magnitude, its area, which is pi times 1 squared. How about the direction of the area? Can you tell me? What's the direction of the area? Remember, it's always perpendicularly out.
So it's in K.
That's K, okay? So that's it. So this one is K, or just pi times K. So the magnetic moment is the current, and then times pi in the K, okay? So this is basically 2 pi in the negative K direction. So the direction of the magnetic moment in this case is negative, is perpendicularly in the direction of the magnetic moment, okay? So this is a very important quantity because it's a number that characterizes the property of the loop. All right. Next, we're going to look at magnetic potential energy. Magnetic potential energy. What's the relationship between potential energy and work done by conservative force? Do you remember? Work done by conservative force equals?
Negative delta potential energy.
Yeah, negative potential energy. So we can say that the work done by the magnetic force equals the negative of du, and the changing potential energy. So we're going to get the formula for the potential energy. All right. Now, suppose, let's say we have, I don't know if I can go, let's say we have this loop over here, and then there is a magnetic field in the direction of the area of the loop. Okay. So at this time, this is a field. What do you think is the torque acting on the loop? The area and the B are parallel. So what's the torque? The area is this way, the field is parallel. Therefore, this is also the direction of the area perpendicular to it, okay? So if A and B are parallel, what's the torque?
0.
0. If two vectors are parallel, the angle is 0 and sine of 0 is 0. So understand this loop is not experiencing any force, okay? So we have the area going this way, we have the field going this way. How about if I rotate a little bit? Let's say I rotate about this axis like this. So the area is going to be rotated, but the field is still this way, right? So this would be my A. If I rotate it a little bit like this, the area will be rotated. When I rotate the loop, the area is rotated, but the field is not rotated, okay? So the torque is A cross B, right? The direction of, well, let's assume the direction of the current is counterclockwise. So we don't have to worry about the sign. Okay, suppose the current is going this way, all right? So you got the area going this way. When I rotate from A towards B, what happens to the screw? It
Goes
comes
inward.
out. You see that? From A towards B is counterclockwise. So the direction of the torque is up, which means the rotation is counterclockwise. Nice, what did I do? I rotated clockwise, but the magnetic torque is counterclockwise. So it's a restoring force. It's just like a spring. If you push a spring, it pushes against you. Okay, so in this case also, if you move the loop, the magnetic force opposes you. So what this means is the force and the displacement are opposite in direction. If you move this way, the magnetic force opposes you. And if the angle is 180 degree, the work done is negative, right? So the work done by the magnetic field is going to be negative because when I display this way, the force is this way. It opposes, just like a spring, okay? So this work over here is negative, all right? So we can say that dw, let's say du is negative, the work done by the magnetic force. Do you remember the formula for work, for rotational work? Huh? For linear, the formula is what equals force times distance, right? Remember that? For rotational, the force becomes torque, the linear displacement becomes angular displacement, right? So if you remember, this is a formula for torque. I mean, the work done by torque is torque times d theta. Okay. Okay, so now we know the torque, at least its magnitude. Its magnitude is I, A, B, the sine of theta, right? But now we have concluded that the work done by the magnetic field is negative because it's opposite displacement. If I rotate clockwise, the magnetic force opposes me, okay? So I'm going to say this work is the negative of this. So you got I, A, B, sine theta, d theta. I should say dw over here. Okay, so the work done is the negative of this expression. Okay, this is my torque over here, and this is my d theta, right? This is a formula for the torque, and this is d theta, but it should be negative because the magnetic force opposes the displacement. Okay, now let's go to this formula over here. The change in potential energy is the negative of this small amount of work, okay? But we just concluded that is this one, torque times d theta, which is negative I area B sine theta d theta, okay? So the change in potential energy is actually positive. This is the torque, IB sine theta, okay? This is my torque, and then times d theta, okay? So this is the change in potential energy when rotate the loop by an angle d theta, okay? What do you to get the total potential energy? You integrate, right? So we have the integration of I, A, B, sine theta, d theta, okay? What's the integral of sine theta? Well, these are constants, so let's just have IAB, the integral of sine theta d theta. What's the integral of sine theta?
Negative cosine theta.
Negative cosine theta. So we've got negative IAB cosine of theta, but this is an indefinite integral plus a constant, okay? So let's say this is u equals this one plus a free constant, okay, because this is an indefinite integral. But now we're going to define a reference point, okay, to get rid of this constant, all right? To get rid of this constant, we have to define our constant, our reference point in such a way this is zero, okay? If this is zero, then C will be zero. If I define U to be zero at a point where this is zero, then C becomes zero, okay? To get rid of C, I have to define this in such a way cosine of theta is zero. Where is cosine of theta zero?
Pi over 2.
Pi over 2, okay? So let the reference point be, let u at pi over 2 equals 0. In other words, my reference point is going to be pi over 2, okay? So let's do that. You've got u at pi over 2 equals negative I, A, B cosine pi over 2 plus C, okay? This is 0. By definition, this is 0. I'm defining my potential energy to be 0 over here. This implies C is 0, okay? So if I define my potential energy to be 0 at pi over 2, then my formula just becomes this one, okay? So with this reference point, my C is 0. So I've got the following formula. The potential energy, let's say magnetic potential energy, is negative I, A, B cosine of theta. Now, can you help me write this in terms of a vector product? How would I write it?
Dot product.
Very good. So these are, my vectors are, well, first let's write this as mu. This is mu, right? So this would be UB equals the negative of, this is a vector mu over here. Remember that? So this is mu dotted with B, okay? So this is a formula for magnetic potential energy, okay? So magnetic potential energy is the negative of the dot product between the magnetic moment and the magnetic field, okay? So this is a formula for the amount of energy stored by a loop in a magnetic field, okay? So what? So when is this zero? Let's say we have this loop over here. Let's say we have this loop over here. Okay, so what's the direction of the area? In this case, it's K. Okay, the direction of the area is K. So when the magnetic field is K, you said that like this, you will have K dot K, right? So K dot K is 1, but this is negative, so you would have the minimum. So when the area and the magnetic moments are parallel, you will have the minimum energy, right? When they're opposite, that's 180 degree, right? Cosine 100 is negative, and then negative, you get positive, okay? So when mu and B are parallel, you have the minimum potential energy. But when U and B are anti-parallel, you have the maximum kinetic energy. And when it's pi over 2, by definition, 0. Okay? So in this case, let's say the current is counterclockwise. Okay? So the area is this way. If the magnetic field is this way, you get the minimum amount of energy, the negative of maximum, that's the minimum, right? But if I do cross, this is the angle becomes 180, okay? And then I get a negative or negative one becomes positive. You get the maximum, the maximum possible energy. So the minimum energy is stable equilibrium. The maximum energy is unstable equilibrium. Do you remember the difference between stable and unstable from last semester? Let's say you have a valley and a top of a mountain over here. These two objects are rest, but the difference is if you touch this one, it goes away, but this one stays over there if you touch it, okay? So this is stable equilibrium, this is unstable equilibrium. So in this case, when the energy is minimum, you will have stable equilibrium. That's when the mu and the magnetic field are parallel. If they're opposite, you have stable equilibrium. But when they're perpendicular to each other, like this one, in this situation, you see, the let's say it's counterclockwise, the magnetic moment will be perpendicularly out, okay? It will be like this. So the angle between them will be pi over 2. So in this situation, the energy is taken to be positive, okay? But remember, at this position, the torque is maximum. This is the torque is AB sine theta, right? And sine pi over t is 1. So at this position, you'll have the maximum possible torque, but the potential energy, by definition, we just decided to make it 0 over here, okay? So it'll be 0 potential energy at this orientation over here, all right? So this is magnetic potential energy. I don't know if you have an example, but let's say we have the following example. Let's say we have this loop over here. Let's say it's 2, 2. Well, let's say we have crossover here. All right. So what is mu? Mu is I times A, right? Let's say it's 2 amps. So this would be 2, and the area is 4. In what direction? What's the direction of the area? K, right? So the mu is 4K. All right. How about the B? The B is negative K. Let's say it's 5, okay? But it's perpendicularly in. So you've got B is negative 5K, okay? And the energy at this location is negative mu dot B, okay? So that is negative 4K dot with negative 5K, okay? So you get 20, just positive 20, okay? So this is in the unstable position. All right. Next, we're going to look at electromagnetic force. So far we have discussed force for just electricity and force for just magnetic field. How about a charge moving in a place where there is both electric field and magnetic field? That's called electromagnetic force, okay? So electromagnetic force, electromagnetic force. This is force, these electric and magnetic fields. This is force due to electric and magnetic forces and magnetic forces. Okay, so all it is just add them, right? So the net electromagnetic force, if I use this representation over here, EB, electromagnetic force, okay, that will be the sum of the electric force and magnetic force, right? This is electric force, and this is magnetic force, magnetic force, okay? But what is the formula for electric force? Do you remember? In terms of electric field, it is charge times E, right? How about magnetic force? We just defined it today. It is charge V cross B, right? So electromagnetic force is the sum of these two forces. So we have the electromagnetic force acting on a charge is Q times E plus Q V cross B, okay? This is the formula for electromagnetic force. You just add the two forces to get the both magnetic and electric force, okay? So let's demonstrate this by means of an example. I'm going to get the other section. Suppose, let's say, we have electric field that goes this way. Let's say RE is maybe 10 Newton per Coulomb. And let's say we have magnetic field that goes this way. Let's say this is maybe 2 Tesla. That's the J direction. Okay. Now, suppose we have a charge moving this way. Let's say with 100 meters per second. Okay. So V. All right. So what do we have? My velocity is 100 in the I direction. You see that? It's 100 in the I direction. My electric field is also to the right. It is 10 in the I direction, right? And my magnetic field is 2 in the J direction, right? Let's say the charge is, let's say 5 Coulomb, okay? And my charge is 5 Coulomb, all right? So let's calculate the force now. So the electromagnetic force, EB, is QE plus QV cross B, okay? So my charge is 5, maybe in the bracket, the electric field is 10 in the I, and this is the velocity, 100 in the I, crossed with the field, which is 2 in the J, okay? So what do you have? 5, you've got 10 in the I. What is I cross J?
K.
K, so simply 200 in the K direction. So the force acting on this charge is 50 in the I plus 1,000 in the K, okay? So this would be the electromagnetic force acting on this charge, okay? And of course, if you're in the magnetic direction, you can do very easily using Pythagorean theorem and the tan inverse formula, all right? So electromagnetic force simply means you add the electric force and the magnetic force, okay? Now we're going to look at some devices. First, we're going to look at mass spectrometer. Mass spectrometer. This is a device that separates a mixture of charges according to their masses. Okay, so this device separates particles, let's say of identical charges, according to their masses. According to their masses. So this is a device they use to separate particles that have the same amount of charge, but different masses, okay? Let's see how it works. So let's say you have this field which is perpendicularly out, okay? So we've got perpendicularly out over here. Now, what happens if you propel a charge, let's say the charge is q, with a velocity v, okay? So as soon as it enters the field, there's going to be this force, Fb equals qv cross b, right? So the velocity is to the right, the field is up, okay? So the field is to the right, so you're going to rotate from right to up. That is counterclockwise, right? So it comes down. Or if you want, this is in the I direction, okay? The field is in the k direction. What is I cross k? Is negative j, right? So it will be deflected. But remember, this, as soon as it enters, it will be deflected. But now it changes the velocity, again deflected. It'll keep deflecting. This force is perpendicular to the trajectory. If you've got a force perpendicular to the trajectory, the effect is always a circular trajectory. Okay? You remember the formula for the uh, for a particle moving in a circular path? We have two components. We have a radial component. You've got mv squared over r in the negative er direction, and then plus dv by dt in the e theta. I don't know if you remember that, but the effect of this is just to change direction. So the result will be a circular path. If the force is always perpendicular to the trajectory, the resulting trajectory is circular. Okay, so what's going to happen? This is we're going to move in a circular path like this, okay? And then it'll come out over here, all right? The field will just keep deflecting it in a circular path, and eventually will come out over here like this, okay? All right, so the force, let's calculate the force acting on this one, is this one. FB, the magnitude is charge. Well, the angle is 90 degree, right? So this will be QVB. This is a force, okay? Now, this is mass times centripetal acceleration because it's moving in a circular path, right? Do you remember the formula for centripetal acceleration or radial acceleration? This one over here. So this is m v squared over r. Okay, v squared over r is centripetal acceleration, which is acceleration due to change of direction, all right? So we're trying to get an expression for the mass, all right? So let's simplify it. So we have, well, we have mv over r equals qb, okay? And then we get r equals mv over qb. What does it tell you? The radius is a function of the mass. The greater the mass, the greater the radius, okay? Now what happens if you put a mixture of particles over here? Then we have different radius. Some will go this way, the bigger ones will go like this, the bigger ones will go like this, okay? So they will be separated, all right? Because the radius is a function of the mass. The greater the mass, the greater the radius. So you put them together over here, but they come out separately, okay? So that's how this device works. It's called a mass spectrometer. The reason is the radius is a function of the mass of the particles, okay? Next, we're going to look at a device they call cyclotron. Cyclotron. This is a device used to accelerate charges. This is a device used to accelerate charges. Accelerate charges. Okay. So let's see how they do it. Well, they have two half spheres like this. Place it in a magnetic field. Okay. So let's say we have this charge over here. I mean this field over here, just like the one before. Okay. Let's say I have field perpendicular out over here. Now suppose you propel a charge like this. So what they do is they give potential difference between these two. Okay. So let's say you got this charge coming. Let's say it's a positive charge. So when it goes this way, they make this terminal negative. They make this terminal positive. Okay. So it'll be accelerated to this sphere over here. It goes this way. It goes this way, and then of course we'll move in a circle like this, right? And then they accelerate again. They reverse this one. They reverse this to plus and minus. Okay, it goes faster. It goes faster and faster and faster. Eventually, it comes up with a certain value over here. Okay, so let's say the large radiuses are. Okay, they start over here. They alternate this potential difference over here. When it goes this way, they make this negative. When it enters this way, they make one negative, so it will attract it. So this potential difference over here makes it faster and faster. Okay, so you see this formula over here. The radius and the speed are proportional. Do you see that? So the faster it gets, the greater the radius. All right. So eventually, it comes out with a certain radius r. Let's say eventually, let's say they are. So we're just going to use the same thing over here. We have the magnetic force is QVB, okay? And then you've got mv squared, but now we have the final radius r. After all this rotations, you'll have a bigger radius which comes out, okay? So we have this situation over here, all right? So the speed, well, you've got qb equals mv over r. So that tells you the speed is qbr divided by m. So this is by the time it comes out. This radius over here is the radius by the time it comes out, right? So this is the speed you get eventually. So what's the kinetic energy? Well, the kinetic energy by the time it comes out is half m v squared, which is half m, and then you've got the speed qbr over m squared. Okay, you can simplify it if you want. But so you've got half m is going to be 1 over m, and then q squared b squared r squared. Okay, so finally you'll get this energetic particle when it comes out over here. Okay, they do that by accelerating it by providing potential difference between the spheres, and they have to alternate it because it moves in opposite directions every time. Okay, so that's how this device works. It's used to accelerate charges. Pretty much that's what they do when they, when they collide charges in particles. This is the principle they use to accelerate these charges. All right. So finally, we're going to look at Hall effect. Hall effect. This device is used to measure magnetic field. Okay, used to measure magnetic field. To measure magnetic field. So let's see how they do that. Suppose let's say we have this rectangular object over here. Okay, like this. All right, and let's say we're using this coordinate system over here. Let's say this is my z-axis. Let's say this is my x-axis. Let's say this is my y-axis. Okay. Now suppose there is current going this way. Okay, there's current this way, and let's say there is magnetic field going this way. But remember, charges moving in a magnetic field are acted upon by force, right? Which is F equals I V cross B. Okay. Now, what do you call the velocity of this charges? Do you remember? When you provide a current?
Drift velocity?
Drift velocity, very good. So we have a drift velocity over here. All right. So the magnetic force acting on these charges is going to be this one. You'll have this force over here. You've got Q, the drift velocity. Well, they're perpendicular to each other. So well, let me put them in forms of vectors. So this is FB is Q V cross B. This velocity crossed with B. We're going to assume the charges are moving are positive charges. Okay, so we're going to assume Q is positive. So what's VD? VD is in the J direction. You see that it's going this way. So this equals drift velocity in the J direction. The magnetic field is in the K direction, right? So you've got this equals B in the K direction, right? So what's the force acting on this one? Is Q, which is simply positive, and then VD in the J direction crossed with B in the K direction. Okay, so you get Q, drift velocity, times B. What is J cross K?
I.
J cross K?
I.
I, very good. So this is I. Okay, so the magnetic force is pushing, this is the I direction over here. Okay, this is I direction, J direction, K direction over here. So these charges are being pushed to the I direction. So what's going to do is you're going to have positive charge on this side over here. And then we're going to have negative charge on this side. Okay, so what does it do? It gives another field, electric field. When you separate charges, you got electric field. So you have electric field that goes in the other direction. Okay, you have this electric field goes over here. So you're going to have two forces. So the electric force is Q times the electric field. Okay, so you see these charges are being subjected to two forces. So magnetic force that pushes charge this way, but the electric force pushes charges this way in opposite directions. So until when do you think this buildup continues? It will continue until both forces are balanced. Okay, you got two forces, magnetic force pushing them this way. This is magnetic force. You got electric force pushing them this way. So this buildup continues until the electric force balances the magnetic force. Okay, so the buildup of charges, continues until the electric force balances the magnetic force. Electric force balances the magnetic force. Okay, now let the balancing electric field be EH. Okay, whole electric field. Let the balancing electric field be EH. Okay, so we're saying is the electric field QEH is equal to the magnetic force QBDB. When this happens, there'll be equilibrium. Okay, after that, the charge will not be deflected because they're being acted by two forces in opposite directions. Okay, so what do we have? The B, the electric field, the charge goes away, is electric field divided by the drift velocity. This is it. The magnetic field simply the whole electric field divided by the drift velocity. But what we can measure is potential difference, right? So what's the relationship between potential difference and electric field? Do you remember? Potential difference, H, is electrical times distance, right? So this is the potential difference is EH times D. Now the D is this one, this distance over here, separation of the charges, okay? So this one over here, let's put on this side, this one over here is D, the separation between the charges, all right? So with that, we can say EH is, well, delta VH over D, delta VH over D. So you've got the following. This is delta VH, the potential difference. You can measure this very easily with a voltmeter. So this is measurable. And then we have over D. Okay, so we've got D times VD. Okay, that's it. And we've seen before how to calculate the drift velocity. Do you remember? What's the formula relating current and drift velocity? You remember? We have current equals concentration of charges times the charge of one carrier times drift velocity times the cross-sectional area. Remember this formula? This is the relationship between current and drift velocity. Okay, so the drift velocity the drift velocity is current divided by concentration of charges, the charge of one carrier, which is basically the electron charge, and then divided by the area. But what is the area? You see, the cross-sectional area is this one. The charges are going this way, right? So this is the cross-sectional area over here, okay? So let's call this one T, okay? So this is D, this is T, so the area is D times T, okay? The area of this rectangle over here. So the charges are going this way. This is my cross-sectional area, right? Okay, so A equals D times T, okay? So the drift velocity is current divided by NQ dt, okay? But remember, we're looking for the magnetic field, okay? So the magnetic field is the following. The magnetic field is the whole potential difference, delta VH, divided by D times drift velocity, okay? But we have this for drift velocity. So you've got delta VH over D, and then drift velocity in the inverse, we're gonna have NQ dt divided by the current, okay? So D goes away, so you get the following formula for the magnetic field. The whole potential difference, and then you've got N QT over here divided by the current, okay? So you see, all I have to do is, well, you know the size of the rectangle, so you know this size over here. This is the charge of the electron. The concentration, we've seen how to calculate it. We've calculated for aluminum. Remember that? You can concentrate using Avogadro number and gram molecular weight. You can calculate this very easily. So all I have to measure is the current and the potential difference, which you can do very easily using a voltmeter and ammeter. And with that, you can calculate the magnetic field very easily, okay? You remember the magnetic field sensor we used it in the classroom last time? That's pretty much how they do it, okay? That's how they measure the magnetic field. All right, so that's it for this chapter. Do you have any questions? Mm-hmm. No? All right then, I'll see you next Tuesday. Bye.
Thank you, Professor.
Okay.